Are there any questions?
Yeah, I had one about the conceptual questions from last Tuesday, I think it was. It was number 13. It was an electric field on a point that there's another charge outside of it emitting another electric charge onto it. Does the value of that matter, or is it constant?
That was the two charges. All right, I have a charge here, another charge at this location.
Yeah.
Does the electric field at this location depend upon the second charge, and does the force depend upon it?
It says on point Q, does the value of Q matter for the electric field?
Okay. And what was your thinking?
I would assume so, depending on how much energy you have, you would emit more energy.
Well, energy depends upon two objects, but the electric field is not dependent on two objects.
So for an electric field of something, is that related to how much energy it has? In my thinking,
No,
I assume.
not really.
Okay.
And remember that a force on some charge, so the electric force on some charge of 1 is going to be equal to the charge of 1 times the electric field. How do I want to notate this? Let's see, at point P, so at P equals the charge of 1 times the electric field at P. So if I know what the electric field is and I know what charge Q is, then I can tell you the force acting on it.
Okay.
However, if Q1 exerts an electric field at point P,
Yeah.
then it will exert a force on itself.
Which doesn't happen.
Yeah. I mean, it would be called an internal force, and internal forces cancel out, so that the net force on it would be 0. It cannot accelerate itself.
Yeah.
Does that answer your question?
Yeah, I think it does.
Okay. All right. Other questions? Okay. So if I have a positive charge here, it creates an electric field that goes away. If I can consider this a point charge, so if point charge, then the electric field is equal to the electrostatic constant. And I'm putting this form just because we're going to slowly transition to the other form of that right there is just K sub E or K sub C, whichever one I'm going to move for. I generally write K sub E or K sub C just because it's less writing. Times Q over R squared R hat. All right, so that's the electric field. Because Q is positive, it's in the positive R hat direction, goes outwards. If Q is negative, it's in the negative R hat direction, which means inwards. If I put a negative charge here, it's going to, from a force point of view, opposites attract. From an electric field point of view, I have an electric field going to the right-ish, to the right, and the negative charges travel opposite. They go upstream. They travel opposite the direction of the electric field, and therefore, from an electric field point of view, it's going to go to the left. From a potential energy point of view, because I don't think I got into the explanation for potential energy about why opposites attract and like repels. Or did I? I got a couple of heads suddenly shaking no. I know that, well, let's make this positive for this example. I have this negative positive charge here, and into it I put another positive charge. From an electric field point of view, the electric field's going to the right, positive charges go downstream, it would travel along in the same direction as the electric field. From an energy point of view, I know that the energy is equal to K sub E, or 1 over 4 pi epsilon naught, Q1, Q2 over R squared, plus some constant. For the sake of this, let's go ahead and assume if R equals infinity, U equals 0. In which case that means as R is infinitely large, that U goes to 0, and therefore that constant is 0. If I put the positive charge here, what is its kinetic energy initially?
Like, put it where it is?
This positive charge already sits here, I put another positive charge sitting right there. What is its kinetic energy initially?
0?
It is indeed. And throw the units in there for fun.
Units?
Not as much fun. What are the units of energy?
Joules.
Yeah, there we go. All right. Now, well, let's start to move.
Yes.
There we go. Way to be bold. All right, yeah, it should. If it starts to move, what happens to its kinetic energy? Okay, and if kinetic energy gets bigger, what happens to the potential energy?
It's smaller.
Why?
Watched a neat TikTok on it. It looks fun, but it did show that as kinetic energy grows, the potential energy went down.
Under what situations does, when kinetic energy goes up, does potential energy go down?
All situations?
Excuse me?
You said when does it? When does
Yeah, under what situation?
Like when you're dropping it from a certain height.
Oh, that would do it, yeah.
When you start rolling a cart, I mean,
When I start what?
rolling something.
Well, depends. All right, so let's take this notable pressure. What is its kinetic energy? All right. Did the kinetic energy say 0? I mean, while I was pushing it, did the kinetic energy stay 0?
No.
So kinetic energy went up, since we can't have negative kinetic energy. Did the potential energy drop when the kinetic energy went up?
Yes.
How?
Because it's
Jack's just getting an alibi by walking in front of the camera.
the potential energy means that this is the amount that it could move, and then like the kinetic is it moving, so it moving is now taking up the could moving, and then it has moved, and then it's back to rest, which means it's back to could moving.
What kind of potential energy was it?
Well, there's gravitational potential energy.
Did the gravitational potential energy change?
No. Then there's
Why did the gravitational potential energy not change?
because it's still acting under gravity and the gravity hasn't changed.
What's the formula for gravitational potential energy, assuming the acceleration due to gravity is relatively constant?
MGH.
There we go. All right, so M didn't change. I'm assuming the notebook's mass did not change. Acceleration due to gravity, I assume did not change. Did the height change? All right, so potential energy did not change. Yet the kinetic energy did. Under what situations does, when the kinetic energy goes up, does the potential energy go down?
Or it did. I negative kind of potential energy?
Nope.
Okay.
All right. What are the three work energy relationships?
Work. Total. Equals change in kinetic energy.
All right, we're on a roll. Also known as?
The work total equals change in kinetic.
Work theory, it's something theorem.
Yeah, theoretical work energy theorem. All right. What are the other two?
Work not conservative is a change in mechanical energy.
Change in what?
Mechanical energy.
Okay.
And isn't work conservative equals change in negative, or negative change in potential?
All right, there we go. We're on a roll. So under what situations is energy conserved?
Potential energy?
Well, just throwing out random words here.
All of them, right?
No, we definitely have a change in energy here.
Okay. So when the change in potential energy is negative, the work has been conserved.
Not necessarily. Here's a change in
I was just like trying to say out the last one.
that one.
Yeah.
Well, I mean, as I throw that up into the air, there's an increase in potential energy followed by a decrease in potential energy. Energy was conserved then. It was not conserved then. I see you're a 151 instructor. All two of them made a huge impact at this point in 151.
Is is it conserved when the change in kinetic has the same magnitude as the change in potential?
And opposite sign.
Yeah.
Oh, well, yeah, that would be true. That's when, oh, let's go down that route. If delta K equals negative delta U, what's the total change in energy?
0.
All right, and from this, when the total change in energy is 0, what else is 0?
The work.
Which kind?
The total.
The non-conserved.
No, you can still, I didn't say this was 0.
Alright. The non-conserved.
Yes. So energy is not conserved when non-conservative work is done. When is non-conservative work done?
When there's a change in energy.
When there's a change in kinetic energy and not a change in potential energy.
You were both not wrong. When is there non-conservative work? Ignore energy piece of it.
When there's a non-conservative force.
Yes. Okay. Now, back to our problem. Under what situations does, when kinetic energy go up, I know potential energy is going to go down?
When there's a non-conservative force is acted on it.
Just the opposite.
Conservative.
When do I know when kinetic energy goes up, does potential energy go down?
When a conservative force acts on it.
Yes. What kind of force is involved here?
Magnetic.
Or the other one?
Electric.
That's the one. Is electric force conservative?
Yes.
How do we know?
Write it down somewhere.
Okay. Also, there's a potential energy formula. Conservative force, for every conservative force, there's a potential energy formula. We have a potential energy formula, therefore, logically, that does not necessarily hold if A then B does not mean if B then A necessarily, but it does in this case. If there's potential energy, here we go, let's cover it both. There is a potential energy formula if and only if there is a conservative force. Now it goes both ways. So, as the kinetic energy goes up, which we've established, this will start to move, kinetic energy will go up, potential energy will go down because the force is conservative, and we know it's conservative, number one, because I said so. 2, there's a potential energy formula here. So, as it moves, I know potential energy needs to drop. Well, the Q's and the K are not changing in this problem. R will. So as R gets bigger,
It gets smaller.
what gets smaller?
The U.
The total, the U.
Okay. Because if the denominator gets bigger and the numerator stays the same, the whole fraction gets indeed smaller. So from a potential energy point of view, the positive charge will move away from the other positive charge in order to reduce the potential energy. 3 explanations for why the positive charges will repel. Don't worry, there's a 4th. All right, so now let's take a look at this as a negative charge. Using the magic of an eraser. Now, if R gets bigger, my fraction gets smaller, wouldn't that mean that the negative charge would also go away?
No.
All right. How do you, what you're thinking there?
Because the R is the distance, correct?
Yes.
So if the distance is smaller between the plus and the minus, they're getting closer. So it would just be the opposite of the positive one.
So as R gets smaller, doesn't the fraction get larger?
No.
So we're increasing potential energy?
No.
So, there's not a problem here. The question is, why is this not a problem? Because I know that the negative charge will get closer, but how is it that this fraction, as R gets smaller, how does this fraction get smaller also?
Do you have to have a constant or no?
Oh, the plus C? That wouldn't change it.
Oh, because it's gonna be overall negative, and because then, so R squared will get smaller, which will make it more negative, which will make it
Indeed.
get smaller.
Yeah. So it'd be like it's going from -1 to -2 to -50, whatever it gets to. It is becoming indeed more and more negative. If they are opposite charges, the whole fraction is negative. Therefore, as R gets smaller, it becomes more and more negative. In other words, it gets smaller. Questions to hear?
So, how would R get bigger to make the whole fraction? Wait, never mind, no,
Okay.
my question didn't make sense.
I think
So,
no.
what you just said, for that to be true, does Q1 and 2 have to be negative, or should they be positive?
Well, one's negative, one's positive.
Okay. And then R is just whatever it is.
Yes. All right, so we now have 3 explanations for why opposites attract like repels. You will pump for 4 of them. Yes. We get into potential. So I know that the electric potential is equal to some charge times, oops, that's working backwards. Change in potential energy is equal to Q times change in potential. And from that, we sort of approximately, we go with U is equal to QV. The book, I think, has it written this way, but technically that's not right without additional information, such as when R goes to infinity, V equals 0 units. What are the units of potential?
Joules.
It is not.
Newton coulombs.
No. That would be a joule.
Joules per coulomb,
Joules per coulomb, otherwise known as
volts.
volts. So we have V equals 0 V, where those two V's do not mean the same thing. One is electric potential, the other one is the unit volts. But again, this is the relationship between U and V, and this is a pseudo relationship between U and V. Watch out for trick questions there. Now, if I have a positive charge here, whoa, it suddenly changed to black. And then yellow. As I get farther away from my positive charge, what happens to the electric potential?
It gets smaller.
Okay. Not to scale. If I put a positive charge here, which way is that positive charge going to go? Okay.
To the right.
So we can generalize it that positive charges will move to a lower potential. And if we think about that, when Ben Franklin was coming up with the convention, that he was likening it to water, and water flows to a lower potential energy. And he thought of electricity as some sort of positive fluid. Thus we use the word current when talking about electrical charges moving. So positive charges move to a lower potential. This fits in with the 18th century vision or view of what charge flow was. So positive charges move to lower potential. This is not potential energy, this is just potential. If I put an electron here, which way is the electron going to go?
The opposite, up current.
All right. Negative charges